Here we are again, talking about bond dissociation enthalpies. It never ends, does it? Okay, so as I mentioned to you in the previous video, we did see that generally speaking, when you have a methyl or a primary or a secondary or tertiary organic fragment connected to an X fragment, where X could be fluorine, H, OH, CH3, Cl, Br, or I. Generally speaking, you see that the bond dissociation enthalpy is higher for methyl compared to primary, compared to secondary, compared to tertiary, because of the stability of the radicals that you're forming, uh, favoring formation of tertiary as a result of hyperconjugation, and disfavoring methyl radical formation due to the lack of any type of hyperconjugation. But I also pointed out that for the trend, when X happens to be OH, you see a discrepancy, because generally speaking, that bond dissociation enthalpy was decreasing from left to right in the series. But here we see quite the opposite. The actual trend is an increasing in bond dissociation enthalpy, going from methyl to primary to secondary, and kind of like plateaus at the tertiary stage. So I kind of want to explain to you why that happens. In order to do this, however, we need to consider the actual shape of those alcohol molecules, right? So remember, we are discussing the homolytic cleavage of that RO bond in your alcohol, right, forming radicals. And we know that tertiary radicals are more stable. So we're going to try to explain why it is that we're getting the higher bond dissociation enthalpies for secondary and tertiary compared to methyl and the primary alcohols. So as you can see in the structures right here, the different functionalities are drawn in the correct Vesper shape. Oxygen with two lone pairs bears a bent shape, and your carbon with four bonds around it bears the tetrahedral shape. Okay, so I did happen to draw them in this fashion because this kind of lines it up perfectly. You may recall from our first lecture series that when you do have bonds between um, highly electronegative elements like oxygen and elements that have low electronegativity like hydrogen, you generate, generally speaking, low energy LUMOS, the lowest unoccupied molecular orbitals. And this is in essence the acidic portion of the molecule to some extent, right? All right, so now if you look carefully at what I have right here, that LUMO is going on a diagonal, right? If you look at it from left to right, the diagonal has a positive slope. And not only that, but that positive slope lines up nicely with this carbon-hydrogen bond down here. And since the carbon-hydrogen bond is of low electronegativity difference, and it's fully covalent bond, that represents your highest occupied molecular orbital. And so what's happening in each one of these situations is that you have the HOMO donating electron density to the LUMO of that OH functionality. And because you have now this interaction of electron donation from one orbital to another, that serves to lock in place that bond. And via this effect, you're actually making the bond stronger, even though the change from methyl to um, um, primary to secondary is kind of doing the opposite, right? You're trying to make the bond dissociation a little bit more weaker, right, as a result of forming that radical. So the ultimate outcome is that because you have no extra alkyls present on this central carbon, the donation is, to some extent okay in the methyl case. In your primary case, you actually have um, a donation that's even greater. And that's because these CH3 groups tend to pumping a little bit more electron density. So this bond has a bit more of an incentive to donate more electron density. And then this one, the secondary one, has two alkyl groups that donate even more electron density to this overall HOMO orbital. So you have even more donation. So what you're basically seeing is that you're locking that bond in place more and more and more, and that's represented by the bond dissociation enthalpies increasing in this trend. Now, what ends up happening with the tertiary is a similar explanation, but notice that in the tertiary alcohol, you no longer have the carbon-hydrogen bond, right? So whereas before, you were forming kind of a nice little HOMO-LUMO molecular orbital, here is a little bit different because this is no longer a HOMO-LUMO interaction between a carbon-hydrogen bond, but rather between a carbon-carbon bond and the LUMO of the OH. So what could be happening right here is that you have a little bit of an overlap that's not very good. You have a poor overlap compared to the CH bond. I'm not saying that this overlap is terrible. All I'm saying is that it's not as good as the CH overlap, making that the HOMO versus the LUMO. So this explains why you cannot plateau at this case, because by all intents and purposes, the electron density right here should be the highest, but it is a different type of bond. So it's a little bit of comparing apples to oranges at that instance. But with this explanation, this frontier orbital explanation, you can tell why it is that your RO bond is giving you the opposite trend. And it's kind of a beautiful example of how thinking about your LUMOS and your HOMOS and your molecules can actually explain things, because hybridization wouldn't be able to explain this. Resonance definitely doesn't even play a role in this at all. So it really falls on molecular orbital theory to explain to us what's happening to the molecules. And that in and of itself requires that we draw each one of these fragments with the correct Vesper shape. It's kind of important to point that out. Okay, now the last part in relation to bond dissociation enthalpies that I want to discuss with you guys before we get into the actual mechanisms and the calculations is that depending upon what kind of fragment that hydrogen is bound to on your carbon molecule, you have also a difference in the bond dissociation enthalpy. And what you're going to see right here is that if the fragment is an alkyne and it is that the hydrogen is bound to that carbon of the alkyne, you have the bond enthalpy of dissociation with the highest value. And that's higher than if the CH bond is that of an aromatic group, which itself is slightly higher than that of an alkene functionality. After that, towards the lower end, we have tertiary CH bonds, and then we have this other CH bond that is next to an alkene, also known as allylic. So the one thing that you may have already noticed is that the carbons in question are sp for the alkyne, which has the greatest amount of S content. The aromatics and the alkenes, which are roughly in the same vicinity, are sp2 carbons, which have a lesser amount of S content. And then the last ones are sp3 in hybridization, which have the least amount of S content. So if you think about it, carbon being sp with 50% S content means that it has the most opportunities to have its electrons see the full extent of the charge of the nucleus to some small degree, but it is a greater extent than you would have in the sp2 and sp3 hybridizations. So seeing that extra positive charge allows the bond with its electrons to want to be closer, to want to be stuck there for a longer period of time, if you will. So ultimately what this means is that you're going to have the most Coulombic attraction between those electrons in the covalent bond, the CH bond, and the hybridized sp carbon. And for your sp2 carbons, you kind of have an intermediate effect because you have lesser S content, and those that are sp3, you have the least amount. But it is worth pointing out that in addition to the hybridization argument, you also have the stabilization of the radical via the actual hyperconjugation. And in the case of the last molecule right here, you actually have a resonance argument that you can make. You can draw a resonance for this molecule that shows that you can relocate that single electron and thus stabilize the molecule. Okay, now that we have talked about all of that, we are going to begin talking about the actual reactions and the mechanisms of radical reactions. We will utilize some of these values that we have talked about and rationalize up until this point, but I want to save that for the next video. So I'll see you in the next video. Bye bye.